Now, we've also seen a nice recipe for applying Ampere's law. Just to review very quickly, it's very analogous to what we do in the case for using Gauss's law for calculating electric fields. There are a few things I'd like to emphasize, though. The first step always is, again, we use a fluid model to allow us to sketch the field lines. The point of that is it then allows us to carry out the second step, which is to choose an appropriate Amperian loop, which has to do four things, actually. It needs to include the point of interest, so we learn something about the field at the location we're trying to compute it. To make the dot products and integrals easy, we want our Amperian loop to be always either parallel or perpendicular to the field lines. The third issue is that this closed loop has to include some of the current, otherwise we'll be just getting 0 equals 0. And the final thing to keep in mind is that this Amperian loop has to be a closed loop. Just like the Gaussian surface had to be closed, this has to be a closed loop that loops back onto itself. The third step, of course, is we then apply Ampere's law with right-hand rule number 2, meaning that when we determine the signs of the currents and the various fluxes that we have to calculate, we have to use right-hand rule 2 to determine what is the positive sense of the current going through the area. And finally, what we've said so far is that we should be dropping this mysterious displacement current term. Here, if I go up and look at Maxwell's equations as we have them so far, there is this additional term in Ampere's law. In addition to the explicit current, there's this so-called displacement current term. We can ignore it generally for two different reasons. The first reason is that this mu naught epsilon naught is a very tiny number, which makes this term generally negligible. The second reason is that if we are in a steady state situation where things are not changing in time, and we frequently are in just that type of a situation, if things aren't changing in time, then the electric flux through any surface would be constant, so that this time derivative would give us 0, and that's another reason why we can generally ignore that displacement current term. So in terms of our recipe for following Ampere's law, we want to be able to drop the displacement current, particularly for steady state situations. So especially if steady state. And even if it's not steady state, usually mu naught epsilon naught is such a small value that we can ignore the term anyway.